Why? Because we do integration. Your answer is correct, but justification has to be there. You are saying property, very correct. But as I said, work done is not a property. Because work is nothing but integral P dV, right? Because of the integrate is not a property. So our fugacity RT ln f by P, which is P tending to 0 to T, V minus RT by E prime, EP prime. The integral. Then why can I say that this is a property? Because integral. No? Any answer?
So whichever path we follow,
we say. The point is, it is not whichever path. The path is fixed here. The path is, this is the path. This is the P tending to 0. We have to go this way. Or if you follow the equation of state, you go by this way. And we have proved that there are two paths. Either the path you follow, you take up, you will get the same answer. Because this integral is Maxwell equality error. So that's why this is property. Because we have two paths, whatever the path, if Maxwell equality is not valid, this is a big question, whether the focus is the property or not. So, we'll be talking now something we have done earlier, which is Clausius-Clapeyron equation. Have you heard about this? What is Clausius-Clapeyron equation? We're talking about Clausius-Clapeyron equation. What is that? What is that? Not much idea, right? Philosophically, no idea. Okay. I'll give you first philosophical idea. We have our favorite diagram, right? The PV diagram. This is at T1. This is at T2. And this is P sat at T1. And this is P sat at T2. And here, so this P sat is changing with temperature, right? This P sat is changing with temperature. At temperature T1 you have some value, at temperature T2 you have some other value, right? And what we do for the P sat, we can look at how it is changing at the equilibrium, which is mu vapor equals to mu liquid, vapor liquid. How to estimate this? This is done by Clausius-Clapeyron equation. Found out clear? This is how to estimate how this P set is changing from one temperature to another temperature. We need to have the derivative. And this is nothing but how to estimate the entire equation. This is called Clausius-Clapeyron equation, which talks about dP sat by dt or rho P sat by dt at mu v equals to mu r. Right? So this is your Clausius-Clapeyron equation. Actually, what actually happens if we look at the complete first and transition diagram. We have seen this diagram, right? This is triple point. This pressure. This is volume. And this point is called critical point. Beyond that, everything is gas. Okay. So along this solid vapor equilibrium, along this liquid vapor equilibrium, along this solid liquid equilibrium, and this point is called triple point, solid liquid vapor, all are equilibrium. Okay. And what we have done here, we have taken liquid vapor zone and put it here. If you look at the pressure versus this is actually temperature, this gives you directly idea of dP. Slope will give the idea of dP sat by dt, right? Along the line, pressure is P sat. Along this line, pressure is P sat. saturation pressure. Right? If you draw tangent, it will be dp sat by dt. What is actually happening? Actual picture is this, in this diagram, PV diagram. Right? So point is, if I get saturation pressure at one temperature, you know, for generally standard temperature and all, we can actually have saturation pressure. If you change the temperature, instead of going to this diagram, you can directly estimate the modified another saturation pressure, another temperature. And this slope, this line, what it does, the coexistence curve in the PT plane. Coexistence curve in the PT. And the slope is giving the slope of this, the tangent, as I said, which is dou p sat by dou t at equilibrium. This is BL equilibrium. We can say BL equilibrium. The tangent is giving dou p sat by dou t. Okay, the tangent is giving dou p sat by dou t. So for the two phases, so this dou p sat by dou t, it could be there for solid liquid. It could be there for solid paper also. Right? I am just doing for paper liquid because you have seen the diagram. This kind of diagram is also there for solid liquid. Metallurgy is talking about solid liquid. Metallurgy is even talking about solid also. Alpha phase, beta phase, gamma phase. So if you talk about metallurgical thermodynamics, they also the same principle. They also have to know viscosity. They also have the equilibrium. Because if you look at the phase diagram is very, very complicated. I remember like this, and all those things will be there. You take the point and all those things. You have very complicated phase diagram. Our phase diagram is ours is very straightforward. Ours is, if you talk about like this, or sometimes you have agiograph, all those things. But there are so much problem. They will have branch like dendrite formations and all those things will be there. It is very, very complicated. But it's still the same thermodynamics principle. It will vary for metallurgical thermodynamics. Okay, so if I consider for two phases, 1 and 2, for two phases, 1 and 2, we have mu1 equals to mu2. Okay, and of course we know the pressure and temperature are same. Two phases, equilibrium, P1 equals to P2, P1 equals to P2, equilibrium, no question. And if I say mu1 equals to mu2, then say G1 equals to G, gives energy and chemical potential both the same. Gives energy and chemical potential both the same. We have to calculate, remember that? We have to calculate dp sat by dou t, dou p sat by dou t. Okay? To calculate dou p sat by dou t. We have the formula dg equals to minus s dt plus vdt that we have seen. Combined first and second order from Reynolds. Linear transformation. So this also you can write as d mu minus s dt plus vt. So d mu 1 2, if I say that two equilibrium process, d mu 1 2, you can write this as minus s 1 2 dt plus v 1 2 dt. Okay. So this is I am saying equation number 1. This I am saying equation number 2. This I am saying equation number 2. 1 and 2, both are 1, 2 could be solid liquid, solid vapor, solid vapor, liquid, whatever. And at equilibrium d1 2, you can say minus s1 dt v1 2. Talking about the equilibrium process. Two phase we are talking about. Now we can define a function Fn, which is nothing but mu1 at temperature pressure minus mu2 temperature pressure. Of course, this equals to 0 at equilibrium, right? This is 0 at equilibrium. Correct? So far everything is going fine. We have not done anything new. All those things are known to us. This expression is known to us and d mu also known to us. We can have differential here. dfn, which is d mu1 Tp minus d mu2 Tp, equation number 4a. And if Fn Tp, which is mu1 Tp minus mu2 Tp equals to 0, we will get P sat, which is P1. See, what you have to find out? You have to find out dou P dou T, right? A saturation point, right? Coexistence. You have to find out dou P dou T, dou P dou T at coexistence. We have to find out dou P dou T at mu v equals to mu L or mu1 equals to mu2 or mu1 minus mu2, which is the function. The function is 0, Fn equals to 0 at equilibrium. Okay. What to write? Implicit function theorem? Yes. What should I write in implicit function theorem? Minus dou Fn by at fixed P by dou Fn by T. Equation number 5. So first part, numerator part, dou Fn by dou T at fixed P. What you will get? You will get dou mu1 by dou T at fixed P minus dou mu2 by dou T at fixed P. You have the equation number 2. Dou mu by dou T is minus S. Equation number 2, you can see it's minus S. So it is minus S1 minus minus S2. Equation number 5a. Dou Fn by dou P at fixed T. What will you get? What will you get? Dou Fn by dou P at fixed T temperature. What will you get? V1 minus V1 minus V2, equation 5b, right? Now combine equation 5a and 5b, combine equation 5a and 5b, what will you get? So you get dou P Fn equals to S1 minus S2 by V1 minus V2. Why? Because of the negative sign, things will be similar. This is nothing but dou P 1, 2. We can write this as, and this is equals to mu 1 equals to mu 2. Equation number 8. You got some expression. Dou p by dou t at Fn. Fn is the mu 1 minus mu 2. Of course, this when dou p will change, situation of Fn also will change. Fn cannot be all the time 0 because Fn is 0 at this point. Fn equals to 0. At this point Fn equals to 0. When you are traveling, Fn is not 0. Fn has some value. Okay? Mu b minus mu l. Some value is there. But at this point it is 0. Right? We can calculate at this point. We can calculate at this point. Okay? If you say at this point what is the value? What is the value? You can calculate. But this Fn is nothing but mu b minus mu l. This Fn equals to 0 at the saturation point in a particular point. Okay? So, how to estimate? How to estimate this quantity? S1 minus S2 and V1 minus V2. How to get process? Did you already derive process Clapeyron equation? Yes or no? We have not derived process Clapeyron equation. This is the fundamental. So, how to estimate? How to estimate this quantity? How to estimate this quantity? If you remember vaguely that process Clapeyron equation is something from heat of vaporization, right? Right hand side. How it will come? How this will come? S1 minus S2. There is no del here. S1 minus S2 is here. I don't see del in here. We have heat of vaporization outside right hand side, right? Process Clapeyron equation. How to get it? So H equals to G equals to H minus Ts. H equals G plus Ts. So what we will have? H1 minus H2 equals to what will you have? H1 minus H2 equals to, because heat of vaporization is an estimate. It is there in the table, heat of vaporization. Pardon?
G1 minus G2.
What is G1 minus G2? What is that?
G1 minus G2.
G1 minus G2 is what? 0. Equilibrium. So it is T into S minus S1 minus S2. Same temperature at equilibrium. Temperature is same. At equilibrium, vapor and liquid have the same temperature. Okay? So we have S1 minus S2, which is H1 minus H2 by T. So this equation will boil down to dou P dou T Fn equals to, or you can say 1, 2 and mu 1 equals to mu 2. It will be H1 minus H2 by T into V1 minus V. H1 minus H2 for heat of vaporization for VLE, delta HV. If 1 is liquid and 2 is vapor, then H1 minus H2, it will be delta HV, heat of vaporization. Right? That is called heat of vaporization. Heat of vaporization is defined that you have enthalpy of liquid, enthalpy of vapor, you subtract it, you get, they add the equilibrium. At the equilibrium is heat of vaporization. Right? So, you can write dP sat by dt at equilibrium mu B equals to mu L, which is delta H vapor divided by T into V minus VL. This one is V. Of course, one has to be V because otherwise a negative quantity. Better. I don't want. In that case, you have to talk about negative beta vaporization. I don't want. So V1 minus V2, I want to have 1V. L is second phase, the VV1 minus V2 is always positive. And in general, VV is much greater than VL. At least one order magnitude higher. And if my saturation pressure is low, so that I can assume that V behaves ideally. That means at low pressure, we can assume VB as RT by P, right? At low pressure, it is not valid for the high pressure. That means you can see the limitation of Clausius-Clapeyron equation. At low pressure, we are assuming that volume of vapor is much higher than volume of liquid. Then you are having the fundamentals of Clausius-Clapeyron equation. So Clausius-Clapeyron equation based on these two assumptions, and what we are getting finally? dP sat by dt, which is, we can see that delta H vaporization is there. We have RT squared, we have P sat. Am I correct? This P sat, saturation pressure, and this is not the Clausius-Clapeyron equation. Then you have to integrate. So this equation you might have seen earlier, right? We have seen this equation. So these are fundamentals. So it's a vapor-liquid equilibrium, okay? And vapor volume is much higher than liquid volume. If they are not, then you have different sort of equation, okay? And system is sufficiently low pressure. Remember that Clausius-Clapeyron equation cannot be applied if the system pressure is not sufficiently small. Clausius-Clapeyron equation cannot be applied if the system. Some people are actually thinking something else, they are not writing, but some are writing. It is good for me. At least what I am shouting, people are writing. So Clausius-Clapeyron equation cannot be applied if the system pressure is not sufficiently small. Okay. So if you have the dP sat by P, this dln P sat, right? So if you integrate, what you get? ln P sat T2 by P sat T1. What's the right hand side? Remember that this equation I got from, if you take it here, it will be dln P sat, and then delta is where RT squared dt. Take the integral T1 to T2. What will you get? 1 by T2. But it is, right hand side is what? 1 by T1 minus 1 by T2? No. Right hand side is something else. What is right hand side? Right hand side is what? Just one hand please. Who can volunteer? One hand please. One hand. Yes.
Delta H by R.
Delta H vapor by R.
1 by T1.
You can put
1 by T2.
minus L. This is Clausius-Clapeyron equation. Now you can understand the basics of Clausius-Clapeyron equation. In the saturation pressure, people say vapor pressure, saturated pressure, or vapor pressure. Yes. Pardon? Heat of vaporization. Heat of vaporization, actually, you can see that variation of heat of vaporization, it is negligible with temperature. The long range of temperature, if you look at the table, don't believe me, look at the table, that heat of vaporization doesn't change. Okay? So you assume that this T1 and T2 they are sufficiently close. Another assumption we are giving. And with that range, heat of vaporization is not changing. Otherwise, you cannot take it outside the integral. You take inside the integral. An integral in that case very complicated, and you have to solve by numerical instead in that case. So in that case you won't get this Clausius-Clapeyron equation, you get some kind of numerical form. Okay? One up here. Because P-sat is not changed. P-sat is not constant. P-sat is changing. You are changing P-sat. Only heat of evaporation is constant. R is constant. No problem. Heat of evaporation can be constant if T2 and T1 are sufficiently close. The very high temperature difference, then they can be changed. Okay. So this is the fundamental of Clausius-Clapeyron equation, and if you look at this will, in fact, you can look at this equation, P ln P sat, which is delta H vapor by RT square E. That's the way we actually. And you can write this as ln P sat as minus delta H vapor by RT plus C. Another form. C is the integration constant. Okay. From there also you can get this form. Whatever way. This is the form, very interesting form. You can have semi-log plot. You might have seen log plot, semi-log plot, linear plot. Linear plot is very much comfortable. Why semi-log plot? Because you can see that if I say y equals to ln P sat and x equals to 1 by t. So then it is like y equals to x plus c. That means what? That means semi-log plot is logarithmic, this is linear. Okay, semi-log plot you might have seen. ln P sat and putting 1 by t, how your graph will look like? How will your graph look like? Linear. How it will be? Okay. So we can write ln P sat equals to A minus B by T. C is replaced by A and this entire thing replaced by B. So many things you are getting. ln P sat equals to A minus B by T. Okay? It is not exactly Antoine equation. Antoine equation has a correction, some C. Okay? Antoine equation says some correction will be there. And why? Because heat of evaporation will be having some dependency, as Rahul said. So for that thing, they will say some kind of, and that will be depending on different system. R is a molar gas constant, but heat of evaporation is not constant for water or ethyl alcohol, whatever. For different system, heat of evaporation, different things. So for that purpose, we need to have some correction. So this will be changing it with material. This is also changing with material. So this is nothing but so now we have derived Antoine equation also. I am sure you have not derived earlier, the first time, right? Any of you derived earlier? The first time. This is Antoine. You might have seen Antoine equation, right? So this is Antoine equation. Antoine equation is a consequence of Clausius-Clapeyron equation. Antoine equation is a consequence of Clausius-Clapeyron equation. So correlate the vapor pressure accurately over the range 1 to 200 kilopascal. If you go home, go to Sandler's book. Sandler has a table for different materials. It is giving A, B, and C. water, ether alcohol, many other materials. It will give A, B and C. If you take all A, B, C, this equation will give for a particular temperature saturation pressure. The point is, as I said, how low? They are saying up to kilopascal you can use it. Up to 200 kilopascal. Beyond that, this may be diverted, because the entire foundation of the proof of this theorem, proof of this equation is based on the fact that saturation, the entire pressure, the system, the pressure is pretty low, and they are saying that up to 200 kilopascal it is fine. So further corrections have been made by Riedel and like a Brown equation. So Riedel gave a correction. Riedel equation. They gave some correction, which is ln P sat, which is A plus B by T plus C ln T plus dt to the power 6. Hard bond. Equation ln P sat A plus B by T plus C ln T plus dP sat by T square. Okay, the higher order equations. This is most commonly acceptable. You all use an end-to-end equation. Okay. Now we will go to the assignment problem to apply the Clausius-Clapeyron equation. Up to equation, I think I have given you the fugacity problem, the assignment number 5, using steep tables. Did you calculate the fugacity? Okay, you can try it at home. You have not calculated. Assignment number 6. Problem set 3, assignment 6. The following vapor pressure data are available. Ice temperature, pressure millimeter mercury, -4 3.280, -2 3.880, +2 5.294, +4 is 6.101. Estimate each of the following: heat of sublimation of ice, number B, heat of vaporization of water, number C, heat of fusion of ice, number D, triple point of water. Okay, so we will start based on the Clausius-Clapeyron equation. We won't use entire because we don't have data for A, B and C. So we have to go for the Clausius-Clapeyron equation because for that purpose we have the data for different temperatures. So there are 4 problems. So we have ln P sat T2 by P sat T1 is minus delta H vapor by R 1 by T2 minus 1 by. First problem, heat of sublimation of ice. First problem. Delta H sub by R. So this is actually I have done for the vapor, for other system like solid and vapor means sublimation, right? Solid to vapor. Okay. Solid to liquid is melting. Liquid to vapor is vaporization. Sublimation is solid to vapor. Okay. Solid to vapor. So same equation can be proving, right? Proving same way. 1 to 2 you take, and then in that case H1 minus H2 will be the H sublimation. Okay. What's the answer? Delta H sub by R. What will the unit of that? What is the unit? First determine the unit. Before we do the mistake. First determine the unit. First determine the unit. What will the unit? Delta H sub by R. Unit of delta is sum by R. K, not temperature is not the unit. Temperature is carrier. K is the unit. Yes. K is the unit. Why? Because this will be cancelling the same unit. If you divide by 1 by T2 minus 1 by T1, 1 by Kelvin, it will go as Kelvin. That's the way first I will do before I start the problem. Because I told that in BTech level, I lost 10 marks and that is my turning point. After that, I never forget if I solve a problem, I write the units. Okay, answer. Heat of sublimation of ice. What will be numerator? Minus ln. What is that? Numerator, denominator. Numerator, denominator. What is numerator? If you don't understand, you see the physics of the problem. SLV, am I correct? So you are in this line. Okay? This is temperature scale. This is pressure scale. Please don't try to solve blindly. If you try to solve blindly, is a problem. You have the data here, which is minus 4, which is minus 2. Okay? dP sat by dt is along this. Am I correct? Solid paper line. You have the data at minus 4, saturation pressure. What is that? What is the data at saturation pressure at minus 4? Just 1% please. Don't say 3.280 millimeter mercury. Minus 2, you have 3.880 millimeter mercury, right? So, what are the values here? See, if you draw the picture, everything is clear. This is minus 4, this is minus 2. And I have to follow this path. Okay? How much? What's the numerator, denominator? I am not getting the answer. Numerator, denominator. Man, I am getting shocked. Question is given, you have to just copy the numbers. You cannot copy from the question. I am shocked. Even now you cannot do, you don't know the answer. Numerator, denominator. What's the answer? No, I am not asking you. I gave you the chance. I am actually asking him. Yes. What is that? 3.880. 3.280. I am really surprised. The same thing. I showed the diagram. Nobody taught me like this. That's why I have learned. Nobody taught me. I have never taken thermodynamics at PG level. BTech level, I never learned anything. Maybe that's why I am able to teach here in the class. And that's why you won't be learning because I am teaching in the class. It's all vice versa. Divided by, not Rahul, somebody else, something else. Now everyone can you respond? Yes. No, that's what. You will be giving the excuse. Yes, sorry. Yes, sir. What is that? You do. What is that? 1 by 2. What are you talking? Please. Your unit is degree Kelvin. Remember, sir. What are the denominator values? Who can give the response? That's why. Why are you writing that? Because we never care for writing the units. You never care because we have some numbers. The question you just put the value. You have the calculator. No income tax. Put it. Go home and sleep. That's it. The job is done. The teacher gives bad mark. Okay, teacher is bad. Cutting the marks. What is denominator?
1 by 270.
Just yes. Who is giving the? Please raise the hand. Yes. 1 by 271.15. Correct value. Minus 269, right? 0.15. Yes. How much you are getting? Degree Kelvin 6030 Kelvin. How much is your delta itself? Remember that R is 8.314 joule per mole per degree Kelvin. Put it there and see what unit you are getting. What is that?
3.964 kilos.
3.964.
50.96
kilojoule per 50.97 kilojoule per mole. If you do by unit, you can get it. Yes. Okay, one question I will give here. When I say -4, -2, why I am picking up this branch? I could have picked up this branch also. That question should have come from you. Yeah? Okay, look at the data. What our data is? And if I ask, if you do that, it will be like a fish market. I won't be able to teach the class. When I ask the question, you need to answer. At least our gentleman did the answer, made the point. Plus 2, it is 0, triple point. Plus 2, plus 4, it is 5.294, and this is 6.101. If we have vapor liquid, these values have to be more solid liquid, right? But my values are less, that means it has to be solid vapor branch. That means the data is sufficient to take care. If I am in this branch, my data has to be at least 7 or 7.5 to 8. It has to be more. But my data is given only 3 point something, so this has to be this branch, not this branch. Funda is clear? No. Funda is not clear. Huh? You have the question with you, right? If you have the question, I don't have the question with me. What's the table? What is the data? This is your pressure, right? What is the pressure for the ice? 3.280. You need to have a graph paper. Next is I have to come with a graph paper in the class. Give to everybody graph paper. This is 3.28. This is 3.88. Right? If assuming that this point is so solid, this is your solid liquid curve, right? That will give the melting. Why I am asking for sublimation? Why not melting? Because if this is the melting, that means the data has to be more than 5.295, 6.1. This data, if I collect, this has to be greater than 6. That means this branch has to be in this branch. This is kindergarten level. If you ask me why 3 is less than 6, I have to close, that's all. Close the shop in thermodynamics class. So from the data, we can find out we have the sublimation data or we have the melting data. Not clear? Next question. Heat of vaporization of water. Look at the data. We have sufficient data? Answer is yes. Liquid vapor data is available. Okay? Liquid vapor data is available. How much it is? Question number B. Delta H vaporization by R ln by something. Fill in the blanks. Who will give the answer? Not Rahul. Not Rahul. Yes, madam. 6.101 5.294. You have ready your this thing, your denominator part. What is that? 1 by 277.15 minus 1 by 275.15. Okay, what is delta H vapor? Directly give me the answer.
Nine.
44.98 kilojoule per mole. Now the real question comes. Third question is real question. Heat of fusion of ice, that is melting, solid liquid. I don't have the data. I have the data here, no data here. How to calculate heat of fusion? Delta H fusion. How to calculate heat of fusion? So, we know delta H sublimation, which is H vapor minus H solid, like for H1 minus H2. Delta H evaporation was H1 minus H2. One was vapor phase, two was solid liquid phase, because I don't know P1 minus P2, the P minus P1. Similarly, delta H vapor is H vapor minus H liquid. So delta H fusion will be, in terms of delta H sum and delta H vapor, can you write? Delta H fusion will be what? H liquid minus H solid. Am I correct? So how to get from it heat of evaporation and solid and sublimation? And sublimation? What's the formula? What's the formula? Delta H sublimation minus delta H vapor. Yes, madam. Sublimation minus delta H vapor. Yes. Next step. You have the values. How much is the answer? How much is the answer? It's very straightforward. Just calcium. Put on calcium, you get the answer. Put on calcium, you get the answer. How much? 5.99 kilojoule per mole. 5.99 kilojoule per mole. Last question, D. The triple point of water. You have to find out for this system, what's the triple point? I want the triple point pressure. Triple point pressure and temperature. Temperature you guess around 273, but exact temperature you don't know. We are assuming 273 because that is quite obvious for water. If it is something else, you don't know. You have to calculate triple point, right? Triple point is 0 degree centigrade, you all know that. Is the triple point 0? But exact number I don't know. What's how to get it? So last question is triple point. How to attack? At the triple point, what actually happens? You have got two equations or three equations. You can actually have sublimation and vaporization. We have delta H sum and delta H vaporization, right? So delta H sum by R. So this point you have TT and TT. Triple point temperature, triple point pressure. So you have delta H sub by R, which is 6130. Already we have proved in the first problem. 6130 ln PT by P sub T1 divided by 1 by Tt minus 1 by T1. Equation number A. And what was this value? Delta H evaporation by R. Here, anybody has the value? Saved. I didn't ask for the value. There some value was there, which was how much we have found out? 5410. So delta H vaporization by R, which is 5410, which is minus ln Pt by P sub T2, some other temperature, goes to 1 by Tt minus 1 by T2. These two things are known, because at this point we can approach by this, right? We can even go by this curve, but we don't know that. Why do we have extra calculation? Because we need to have temperature and pressure, two unknowns, two equations are sufficient. Yeah. Two equations are sufficient. Okay, so from these two equations, how to calculate Pt and Tt? Pt and Tt, how to calculate? What will be T1 for the first case? What will be T1? Any idea? Capital T1. Sublimation zone. What is T1? Capital T1. I am just surprised. Just one hand please if you know anything. Not you two. Yes. 259. What temperature? Okay, you can take 271 also. Anything. You can take this also, this. So since this is near, you can take this one, no problem. Otherwise I take the nearby. You'll have less error. This is 271, right? This is 269. I will take this one. Similarly, I will take some point here. What is some point? 275.15. So T2 is 275.15. T1 is 271.15. We have got all the values, unknowns are. So P sub T1 is also known. P sub T2 is also known. So your question is calculate Tt and Pt. Two equations, two unknowns. Calculate Tt and Pt. Two equations, two unknowns. No answer from your side? Only two equations are there and two unknowns. So you can do it by your hand. You divide equation first by second equation. If you divide, you can see the Pt and Pt will get cancelled. You will get only Tt. If you divide equation first by second equation, you can calculate temperature fast. And once temperature is known, you can take one equation and get the Pt. Any one equation you can take. Take the first, divide the first to second equation. 6130 by 5 by 5410 minus ln Pt by P sub T1, P sub T2 is known. So Pt, Pt will get cancelled and we have got only Tt. From there you can get the calculation. How much is the answer? I am just doing spoon feeding like a kindergarten school, a thermodynamics course. Rahul, no answer. I'm really surprised it takes so much of time. You're not doing by hand, you're doing by calculator. First bench, when now we don't have calculator. So far, no answer. Okay, thanks for your kind attention.